The question states that we have a matrix which has the dimensions of m cross n. In this matrix, we need to find a lucky number. And what is a lucky number? A lucky number is such that when considered across a row, it should be the least among everything. When considered across a column, it should be the maximum one. So accordingly, we can see that 3 is the least, 9 is the least, and 15 is the least in its respective rows, and in the columns 15, 16 and 17 are the maximums of the respective columns. So over here we can see that number 15 is the least in its row as well as it is the maximum in its column. So 15 is our answer in the output. Now brute force is kind of easy because the constraints are very the constraints are not very hard. I mean, even an n square or an n power 4 solution can work over here, but coming to the optimal solution is a tricky part. Now we all know that something like when we are given, right, an array, so my first intuition, whatever this optimal solution is, right, brute force, we all know what we need to do. We need to go on each of the elements, and then for each of the element I'll check if it is the least among the rows elements while being the maximum along its column elements का maximum and minimum for each of it. So there are how many m into n elements, and for each of them I'm doing a n plus m operation. Now to pre-process and do this in a better optimal way, we can do is we can take a vector such that all these columns will have row and a column vector, in the sense row vector. So row minimum vector will contain the minimum of each row, and the column maximum vector will contain the maximum of each of the columns. Now it is a O of 1 operation for us to find out this. It will be m into n. To find out this, it will be m into n. But when we are doing for each of the elements, it will again be m into n only and not m into n plus m, because this part will be negated. We have already pre-processed the arrays, which will give us in O of 1 time this value which was being calculated on the fly over there. But over here, when the time complexity was this much, space complexity, we saw that it was O of 1. Over here we are doing that space complexity becomes O of n plus m over here now, because we have two vectors, one with length of n, the other with length of m. So we are just trading off the TC and SC over here. Now coming to the optimal solution, which is the main point of conversation over here, which is the greedy approach also, as you call it, greedy approach. So this approach I did not get on my own. I was very close to the approach, but I did not get on my own. I had to go through multiple of the discussion section as well as the editorial. I followed the Leetcode editorial only, I'll be honest with myself first of all, and I did not get it on my own. I knew that there was something to be done over here, because brute force was not the only way to go about it. So I tried, but I did not get it, because what I was trying is, and I was lazy. First thing I'll say is I was lazy, and the second thing is I did not keep trying on my approach. Whatever I was thinking was, I'll tell you my approach. It was like, if I want to find out the least among these, right? Least among these, suppose it occurs over here, some x, and then I need to make sure that this is the maximum. So I go, and if I find out some y which is more than x, then I'll return that it is not a like what we'll call the lucky number. But and then I was trying that to start from here, so that if we have a monotonic pair or anything, but we do not have a monotonicity over here. So monotonicity is not present. So in some problems what we do is, right, if we have that here it is 1 and here it is 25, and all these numbers over here are increasing and over here also are increasing order, then to find out some number inside that, we can come from a certain direction and travel this in n plus m maximum time complexity. So I was thinking that can we apply that, but there was no monotonicity, so I couldn't apply that also. But then I went through the editorials and then I read about it. So in editorials, anytime any greedy approach is there, what we do is we have to prove it, right? Why does it work? Why does my greedy approach work? So why does it work over here? So let us consider that in some row R1 and this is R2, this is completely whatever the editorial was given. We have x over here and a y over here. Now what I'm going to say, my assumption is that there are two lucky numbers. Is it possible? From this what we can see is, now what I'll consider is, consider this as x dash and this as y dash, or else even better, consider this as a, consider this as b. Now from all the properties we know that for x, consider x first. While considering x, what we see that for x to be the lucky number, we know that in R1 x is highest, sorry, x is lowest, least I mean, which means that b is greater than x. Even now I'm considering x only. Now I know that x is highest in R1, R2 if I'm considering the column, which means in the column consideration. So this is my 1, this is my 2 that I'll be getting is a should supposedly be less than x. So from 1 and 2 what I can say, that x is less than b but x is greater than a, which gives me to the fact that a should be less than b, strictly less, right? Now similarly, when I consider for y, what I will say is in R2 it is the least. When we are considering the row as the entity, it should be the least in the row, which means that y should be less than a is our first inference, and the second inference is with respect to b that it should, y should also be the highest in that column, which means y is greater than b. Now combining 1 and 2, we'll see that y is less than a but greater than b, which means that b is less than a. Now these both things are in direct contradiction. So what we can say is that our assumption is wrong, which means we have proved that there can't be greater than one lucky numbers. Now this is well and good, like this part I understood even in the editorial. Now the next question was, in the editorial what they said was, what they did was, if this is like my R1, R2, R3, right, and C1, C2 and C3, so what they told was that the minimum in R1 row, minimum in R2 row, and the minimum of R3 row. Suppose it was A, B and C. Now what they did was they took the maximum of it. Suppose A is less than B is less than C, just taking a case. So they took C out of this. Now what they considered was maximum of C1, maximum of C2 and maximum of C3. Let us say it was X, Y and Z. They took the minimum, and let us say X is less than Y is less than Z over here. They took the least of it, which was X over here, and now they compared whether C was equal to X or not. And if this was equal, then they said that it had a lucky number which was either X or C, because they both are the same. Or else they returned that return empty vector, like we do not have 0 lucky numbers, right? So this point was where it caught me off guard and I was not able to understand. So I watched some videos also after that on YouTube, and still I was not able to understand like why is it happening, because I was considering a case wherein we say that suppose 1, 3, 15, right, and this is greater, this is greater, this is the greatest, so 2, and then this is the greatest, so let this be 4, and then this is the least among this is that, so let this be 5, and then the least should be something like least should be 6, but the highest these. So what I was considering was, if there is a case wherein I say that 1, 5 and supposedly 15, let's say we have these kind of values, and if I say that in this row this was the least, in this row this was the least, in this row this was the least, how can I be sure that this is the only contender? Because here we were taking C only, right? How come that is the only contender? Because in 5 also, if there was a 5, right, in this row, why can't we have, in this column, why can't we have this to be the maximum? Suppose this was 3. Now again the same thing comes out, proof by contradiction. So this thing was clear. Again I became lazy and I did not try to go deeper about it, and then I just watched a video again to understand it. So I watched 3 videos. 2 of them did not explain why did this happen. It was just intuition for them. For me, it was not. One of them explained, which was Leetcode.io. So that guy had explained it properly. Wherein, if I just take these values, right? Suppose if I take 1 and 5's example itself, I know that 1 is the least in this row, right? And I'm considering that 5 is the least. And what I'm trying to say, that if I have 2 such values in 2 different rows, such that 1 is the least in the R1 all values and 5 is the least in R2 all values, and I have the condition that 5 is greater than 1, of course. Now what I'm trying to say is, let's say that 5 is not a contender, that 1 can still be the answer. I'm just considering that 1 can still be the answer. In that case, what I have is all these values, and all these values are less, all these values are lesser, greater, and this is greater. Suppose let it be 7,8. Now corresponding to this row, right, this column corresponding to this column in the first row itself is satisfying, but in the column we need this to be the highest. We need that 1 to be highest. 1 should be highest, right? Is that possible? Because we know that anything in row 2, 1 could have been anywhere in this, right? Anywhere in the first position, second position, third position, anywhere, I don't care. Now what I need to know is that 5 is greater in the next row, and there are greater elements inside that row. All the other elements are greater than 5. Now if 5 is only greater than 1, then all the other values are also greater, which means that any value which is below 1, any value y which is below 1 will also be greater, which will be in the subset of R2, right? It will be one of the R2 values which was greater than 5. So what I find out is that y is always greater than 1, which brings us to the fact that 1 is not greatest in that column. So if by chance I have in any other row a number which is greater, the minimum number, this is the minimum number of that row, minimum of that row is greater than other rows, then only this can be the contender. We are not telling that this has to be the is a lucky number. No, we are not telling that, we are not considering that. We are just saying it is a contender right now. Now what I need to check, similarly, that in all the columns I find out the maximum. In the similar proof way, what I would say is I will take the least of these and check whether this highest was equal to the least. Highest was equal to the least. So row minimum's maximum value should be equal to column max's minimum value out of all those. Only if this satisfies, we can say that there was one lucky number to be found, or else there was zero lucky number to be found. Because we can again take the same case, right? 1 to 25 if we take, now we know that, and everything is greater monotonic behavior I'm considering, so 1 to 5, and this can be something like 20. In this monotonic behavior, what can we say? That in any row if we take, this is the highest, for this column this is the highest, and for this row this is the least. So for this whole row this is the least, and this is the highest for the column. But when coming to the least, this is the least. So we can say that 20 is our answer over here. But there can be another function wherein we have 1 and 25, where this is the highest of all the row minimums, but this is not the least. So it will be what we'll call it will not come into this category. So that is the proof that we wanted. Again, we have proved by contradiction only that there cannot be a lucky number. There cannot be a lucky number contender, first of all, if there exists a number, a minimum row number which is greater than the other minimum row number. So now if it is greater, then this is the best contender that we have. And why? We had seen it over here. Coming to the code part, it is simple only code part. Where I faced challenges was these things. I was just too hasty to submit. So this part I wrote properly, but then when I came to this part, I have just initialized a loop wherein I am maintaining the int max as the row minimum and then updating it, and then the global maximum of all the minimums, and over here minimum of all maximums. This was for the column behavior, this was for the row behavior, row wise, column wise. Now over here, this is like similar to Leetcode. Whatever Leetcode has given, I've just maintained in that only. Now if I see that if these both are equal, then I return column max minimum. If it is not equal, we know that only 1 or 0 are the number of lucky numbers that are possible. Because 2 was not a possibility, so any number greater than 2 will also not be a possibility. We have proved by contradiction. So hence we are returning a empty array if there was no lucky number found, and the lucky number finding criteria was this is the best contender from all the row elements, row element wise traversal, and this was the best contender for all the column wise traversal. Now if both these contenders are the best contenders, and if they are not equal, then we can just say that it is an empty array. So yeah, that's about it about the discussion. Hope I remember this for a long time. It is marked as easy, but getting this intuition was, I did not get it. So I'm not that great at DSA. I'm still learning, but yeah, eye opener again, that easy problems are the hardest ones. Also when you go to Leetcode also, right, the easy problems have the best editorials in my opinion, And the hard problems have the worst editorials. Best editorials in the sense that they have like n number of approaches first of all, plus the explanation is good in most of them, though this question is an exception. The editorial's explanation was not up to the mark for me, at least. I could not understand it properly, but maybe for others it might have been easier to understand. So yeah, that's it. Hope you like this and hope I remember everything. I've spent quite a lot of time on this easy question now.